Okay, so let me start from page 61. So here, this is actually the end of page 60. Let us concentrate on the spatial ellipsoid for time being. For the time being, the directions of the three areas of the ellipsoid corresponds to the direction along which the stretch delta, lambda, ds over ds is stationary. This is interesting. Stretch is stationary. Okay, so I can say, I think I explained it last time, but see, if you have ellipsoid, something like this, so this is the stretch here. This direction, the stretch is stationary. So here, if this way, the stretch change. So stretch becomes small and large. See here, but for this uh, ellipsoid, axis of ellipsoid, yeah, along the axis of ellipsoid, the stretch is stationary. So that means here it's constant. This is constant. Right? I can change color if you can see better. So here the stretch is stationary, or this axis, if you see this axis, the stretch is stationary. But along somewhere here, the stretch is not stationary. So in one side, stretch is large, the other side, stretch is small. So along the direction of the axis of ellipsoid, a stretch is stationary. If large N is a unit vector pointing in the direction of dx inside ellipsoid, in the undeformed configuration, we have n alpha equal dx alpha ds. Unit vector pointing in the direction of dx. Yeah, I'm, I'm not sure. So you small for large x, now we have a sphere. Yeah, for material coordinate, in material coordinate we have a sphere. Then we want to know the unit vector pointing outside. Direction unit vector of dx. Okay, so this is dx. Okay, so this is dx. This is dx vector. And if we want to know the unit vector, this is like this, dx. You divide by ds. Because ds, I think ds is something like this. Square root dx1 square plus dx2 square plus dx3 square. This is just the length of dx. Yeah. So this is like this. So this is the unit vector. I think it is simple. By dividing equation 564 by ds square, what is it? Let's see. I need 564. Okay, so this is a 564. We divide this by ds square. So this part you just divide. Let's see how this part you divide ds and ds. Yeah. So then this one become n alpha, this one become n beta. So you have this g alpha beta to find the direction. This is so this is more like very strange. Is it okay? G alpha beta. This is more like k square divided by ds square. To find direction n along which lambda n square is stationary, we have to extremize it subject to the condition that n is a unit vector, for such constrained extremization, as discussed in chapter 2, we use the method of Lagrange multipliers and define a new function. What is lambda n? I think we did it before. Lambda n. The question is, what is n? Here we already learned it. We already learned this. N. Yeah. So then we use this. We use this one. So we have lambda n. This is lambda n square. It's strange. We have already done this. To find any direction along which lambda n square is stationary, we have to extremize it. Extremize it subject to condition that n is a unit vector. For such constrained extremization, as discussed in Chapter 2, we use the method of Lagrange multiplier and define a new function f n1, n2, n3 is g alpha beta n alpha n beta minus g n alpha minus 1, where g is a Lagrange multiplier setting f partial na equals 0. We obtain a system of simultaneous equations g alpha beta n alpha n beta minus g na n alpha equals 0. Okay. So where we have used the fact g alpha beta is symmetric. I forgot. Was it symmetric? Anyway, okay, G is symmetric. G is symmetric. G. This is symmetric. So we have like actually if we have G12, N1, N2, we also have G21, N2, N1. So if you take a partial derivative or like this, where if, for example, alpha is 1, you cut this and you cut this. So you will end up having two terms, G12, N2 and G21, N2. But because G is symmetric, you just have 1. And for the second term, you have, this is like n alpha square. N alpha square. So if you take a partial derivative, you will get 2 n alpha. Yeah. So here you have 1, 2, and you also have 2 here. So then you just cancel both 2's. Then you have this one. Yeah. So now we matrix. We make a expanded matrix form is this G11, because beta is a summation convention. So 1, 2, 3. It's 1, 2, 3. G111111. I don't know how we can obtain this. Alpha is also summation. So here, if you have alpha beta 1, 1, which gives this part. So 1, 1, 1, 1, 1, G1. Alpha beta 1, 2. 133. I think you can figure it out. Okay, maybe the easiest way is this. You can see this one actually means this n1 plus n2 plus n3. Yeah. So if you put alpha 1, so if alpha is 1, if this is 1, you have this term here, from here. Otherwise, you have 1, 1, 1, 2, 1, 3. Second term, you have this times n1 plus this one times n2 plus this one times n3. So you have g n2 term because now alpha is 2. Here alpha is 2. So g2, you have this term from here. Same way for this last one, you have n1 here plus n2 plus this one multiplied by n3. Then here you can see alpha is 3 in this case. Alpha is 3. Alpha is 3. I'm sorry, alpha is 3. As you can see, alpha is 3. What is this 3? So, let me see. You have this. This term is here, g and 3. And otherwise, you just have g13n1. Actually, this means g31. g13 equals g31. So g31n1, g32n2, g33n3. Then for this extra one, you have here. So, okay, so this expression, this one-line expression can be expanded to this matrix equation. This is the typical matrix eigenvalue problem for a nominal, non-trivial solution n. We must have determinant g minus gi equals 0. We may expand the determinant to obtain the characteristic equation of the matrix G in the form. I'm not familiar with this. This is three-dimensional matrix. Anyway, so this way. So you have IG1, which is this, IG2, which is this. So it's more like a summation of cofactor. Then you have IG3. IG3 is like this. Then this is a cubic equation. So you have G alpha denote the three roots of cubic 572. They satisfy for some reason. Okay, so this solution satisfies this. Substituting G equals G gamma in equation 570 for each value of gamma, we find a vector n gamma after normalizing it to have unit length. This gives us three directions along which lambda n is stationary. These are called the principal axis of the ellipsoid. I'm a little bit confused. Now we are for symmetric matrix, it is known that these three eigenvectors are mutually orthogonal, or when the cubic has repeated roots, the direction can be selected to be orthogonal, and the eigenvalues G gamma are real. Multiplying G alpha beta gamma equals G alpha gamma by n alpha summation on alpha only. Maybe summation on beta only. Very strange. The word spatial, this is not clear. I think I have to ask Professor now about this. Spatial ellipsoid, is this one? Yeah, I think I have to ask this. This is not so clear to me. This is 61 page, 60 page. See this one? This looks like a material ellipsoid, I would say. See, isn't this material ellipsoid? Oh, this one, right? $564. 564 or this two. 565, 566. Okay, let me make this part clear first. Okay, so I think textbook is very confusing because textbook says let us concentrate on spatial ellipsoid. Right? Spatial ellipsoid sounds like ellipsoid in spatial coordinate, which is this. Okay? That means a sphere in material coordinate. So we should be dealing with this. But then in the next page, we are talking, this book is talking about 564. 564 and this. this is more or less, see this one, blue one, this one, right? So this is more like a material ellipsoid. Material ellipsoid. So it's confusing. Your textbook says we concentrate on spatial ellipsoid, but then equations 565, 66 looks like he is dealing with material ellipsoid. Yeah. So let's make this thing clear first. Okay. Then we move on to the next. So I stop this video here. See you. Okay.